us really some time to present the paper. Thank you very much.
Yes, thank you. They had a conflict of schedule, so they requested me to do it. So, the Zagros and Taurus fault thrust belts formed as a result of the collision zone between the Eurasian and Arabian plates, which started late in the late tertiary, according to Numa. And historic records of seismicity of northern Iraq suggest moderate intensity seismic activity. And the information about the crust has been derived from knowledge of variation of seismic velocities with depth. An accurate knowledge of crustal structure is an important component for understanding geodynamics and the tectonic evolution. Most of the crustal thickness in Iraq is inferred from gravity data, which suggests that the crustal thickness in Iraq ranges between 30 kilometers in the west and 45 kilometers in the east and northeast, according to Al-Sinhabi and Al-Hiti. In 2007, a ground broadband seismic station was installed in Dohuk by University of Arkansas at Little Rock in collaboration with Dohuk University. Since 2007, seismic data from this station has been flowing continuously, analyzed and archived. This data is used in the study to derive a crustal velocity structure beneath the station by using joint inversion of receiver function and surface wave dispersion. On the right-hand side, you see the location of the Dohuk station. The authors used 4 methods to estimate the depth of Moho beneath the station. The first one is HK stacking method. The latter methods are inversion of surface wave dispersion, inversion of receiver function, and joint inversion of both methods. For method 1, they used HK stack program based on Zhu and Kanamori's method, and the other methods, for the other methods, they used computer programs in seismology by Herman. For all immersion processes, a homogeneous health space initial Earth structure model with a shear wave velocity of 4.48 kilometers per second was used in the study. The calculation of receiver function results from isolating the local structure beneath a seismic station from the effects of seismic source structure and the propagation through the mantle of teleseismic events. And the receiver functions in this study are calculated from teleseismic events having epicentral distances that range from 30 to 90 degrees and the magnitudes of 6.2 or larger. Although 96 teleseismic events have been estimated, only 16 of these events these P-wave receiver functions were chosen for the inversion process due to the noisy nature of them, which is shown in table 1. This is the table for the seismic events used to estimate the receiver function, which shows the depth ranges between 10 to 636 kilometers, and the magnitude ranges between 6.2 to 8.5. The first method is the HK stacking technique to estimate the depth of Moho beneath the station, depending on the receiver function, which is introduced by Zhu and Kanamori, to calculate the average depth of Moho, denoted by H here, and the crustal VP over VS ratio, denoted by K here, by using teleseismic receiver functions. And the method depends on assumed P-wave velocity to predict times of the 3 principal crustal reverberations. The method compares the observed amplitudes and arrival times of receiver functions, crustal multiples with the predictions. The best estimates of H and K are found when the main observed Moho phase results in a high peak. From using this method on the individual receiver function solutions, authors found that the average depth is 39.3 kilometers and the ratio is 1.9 for a fixed value of 6.2 kilometers per second. The figure on the right-hand side shows you the individual receiver functions with theoretical onset multiples, which are denoted by red lines with phase names. And the left-hand side shows you the final result of HK stacking method, which for the depth is 40 kilometers and the ratio is 1.9 for a fixed value of 6.2 kilometers per second. The second method they used is inversion of surface wave dispersion, which uses the dispersion curves of Rayleigh and Love waves to estimate a regional crustal structure along the wave propagation path. And excuse me, to estimate the dispersion curves of group velocity of fundamental mode Rayleigh waves, they used local and regional events that have epicentral distances less than 30 degrees and magnitudes equal to or greater than 3. Although they used 49 seismic events, they only chosen 20 events for the immersion process, and these events have epicentral distances ranging from 35 to 639 kilometers, which shown in table 2. These are the seismic events used to estimate the Rayleigh wave group velocity dispersion curves. And the depth, as you see here, is the depth ranges from 2 to 50 kilometers, and the magnitude ranges between 3 to 5.5. 3 to 5.7. And this is the fundamental mode Rayleigh wave group velocity dispersion values, which denoted by the black dots here. And the red line represents the dispersion curve of the inversion process. The Crustal velocity model beneath Dohuk station from the inversion of surface wave dispersion based on the group velocity dispersion curve is shown in the figure. The red line represents the fourth wave velocity of initial model, and the blue line here represents the end model, which authors denoted 3 possible contact regions between 0 to 4 kilometers for the sedimentary thickness and 20 to 30 kilometers for the Conrad discontinuity and 40 to 50 kilometers for the Mohawk depth. The third method they used is the inversion of receiver functions, which they inverted 16 of them for deriving a velocity model on the Dohuk station. This is the result of Crustal velocity model beneath Dohuk station from the inversion of receiver functions. Here again, the red line represents the shear wave velocity of 4.48 kilometers per second, the initial model, and the blue line here represents the finalized model. Again, you can see that the sedimentary thickness column here is around 4 kilometers, and the Conrad discontinuity may be denoted here by 20 to 30 kilometers or 28 kilometers, and the depth of Mohawk ranges between 40 to 44 or 46 kilometers up to here. And finally, they used joint inversion of receiver function and surface wave dispersion by using to obtain more accurate crustal structure model, because it produces a more tightly constrained crustal structure model than using the other methods separately. This is the finalized result for the crustal velocity model beneath Dohuk station from the joint immersion of both methods. And again, the thickness of sedimentary column is around 4 kilometers. Conrad maybe around 20 to 22 kilometers here. The depth of Mohawk is around 38 to maybe 44 kilometers. And this is the results of the weighted joint inversion of receiver function and surface wave dispersion, showing the depth of Mohawk around 40 to 42 kilometers, and the Conrad discontinuity is around 18 to 20 kilometers, and the sedimentary column thickness is 4 kilometers. So the crystalline crustal thickness, which is the depth of Mohawk minus sedimentary thickness at Dohuk station, ranges from 36 to 38 kilometers. According to Paisano